A concept we need for trees are height balance and balance factor. Okay, so we're going to define height balance the following way. We're going to say that a binary search tree is height balanced if for any node in the tree, the heights of the left and right subtrees differ by 0 or 1. Okay, if the heights of the left and right subtrees differ by 0 or 1, we'll call it balanced. If they differ by 0, that means they're the exact same height. If they differ by 1, that means they differ in height by only one level. But if they differ by more than 1, we're going to call that imbalanced, right? And this number that tells us whether they're balanced or not, we call it the balance factor. And the balance factor for a node n in our tree is simply the height of the left subtree minus the height of the right subtree. It's a pretty simple calculation. Okay, and just to help us out with, we need one extra assumption. We'll say that if a node doesn't have a child, right, if it has a null pointer for its left or right child, then that has a height of -1. Okay, so let's calculate some balance factors. So let's start with node 5. Node 5 here is the first entry in my table. So the height of the left subtree, right, if we look at its left side, there's nothing there, there's no child, so by definition, it's -1. Likewise, on its right side, it has no subtree. So by definition, the height of the right subtree is -1. Then we subtract these two, left minus right, to get the balance factor. So in this case, the balance factor is 0. And that makes sense. It's a leaf node. There's nothing beneath it, so it's balanced. It by itself is balanced. I'm going to do this out of order. Let's look at 25. 25, again, is a node that has nothing on either side, right? So it has a left subtree of -1 and a right subtree of -1. So it will also be considered balanced. When we go to 20, 20's left side is -1, but its right side is 1 because it has one child beneath it. Okay, I'm sorry, actually, I'm getting ahead of myself. The height of its right subtree is actually 0 because we look at the height of the node beneath it. Okay, so 25, because 25's height is 0, it's 0 levels from the bottom. Then, whereas this node doesn't exist, so it's like at -1, right? It's beneath 20 by 1. Then what we say is -1 minus 0 is -1, and it has a balance factor of -1. By the way, because we're subtracting, right? We're subtracting the left side from the right side. If we get a positive number, it means our left side is longer. If we get a negative number, it means our right side is longer. So this number -1 is telling us something. It's telling us that since it's telling us that the right side is longer, right? Because it's negative, the right side is longer. Okay, for 15, similar thing. Its left side is -1, but now its right side height is 1 because the height of 20, node 20 is 1. And so now we have -1, -1, and we get -2. And so this is telling us that at 15, it's really lopsided to the right, right? It's really long on the right. And then when we get to 10, the height of its left node is 0. So this tree has a height of 0. And then its right subtree has a height of 2. And so then we say 0 minus 2. And we get a balance factor of -2. So we're again saying that 10 is really heavily slanted toward the right. Okay, so based on our earlier definition, we said anything with a difference of 0 or 1 is balanced. So that means we could consider 5 balanced, and we could consider 20 balanced, and we can consider 25 balanced. But 10 and 15 are not balanced because they exceed that factor of 1, of 0 or 1. And normally when I talk about balance, I'm going to assume absolute value. So it doesn't matter that it's -1 or -2. It's just if it's a 0, absolute value of 0, absolute value of 1, then it's balanced. But anything greater than that is unbalanced. Again, when we calculate this, we calculate the height of the subtree. So it's like like when we're calculating the balance factor of 10, we look at its subtree on the right side and we pretend like that's the only thing we have. And so here, this tree by itself has a height of 0, right? The subtree rooted at 5 has a height of 0. And so that's why we plug in 0 here. And the subtree rooted at 15 has a height of 2. And so that's the right subtree of node 10. And so then we subtract those and we get its balance factor of -2. And again, as I was just saying, a balance factor of 0, 1 is needed on all the nodes to be considered height balanced. And so this tree is not height balanced. So how about these trees? Are these trees balanced or not? Okay, well, if we start working through the math here, what we're going to see is that the nodes at the leaf nodes are always balanced by definition. Okay, B is balanced because its two subtrees have the same height. E is not balanced, but it's only imbalanced by a factor of 1 because this will be -1, this will be 0, -1 minus 0 is -1, and so E is okay. And then when we get to A, we'll also calculate balance. And so the height of its left subtree is 1, and the height of its right subtree is 1. So 1 minus 1 is 0. So this tree over here, this first tree is balanced. All of its nodes have a balance factor of 0 or 1 or -1. Okay, this tree here in the middle is going to be similar. So B and E are going to have balance factors of 1 and -1. And then its root is going to have a balance factor of 0. So this will also be balanced. This tree over here, though, on the other hand, we just add one more node down here at the bottom. This should be G. This should be node G, not a second node F. But anyway, this is not balanced because what's going to happen now is E is going to realize that it has a balance factor of -2. And E is going to throw this whole thing off. Even though A is going to have a balance factor of -1, E is going to have a balance factor of -2. Then that's going to prevent this tree from being balanced. So this is bad, and this would not count as a balanced tree. Okay, so how can we calculate this balance factor? Well, if we go back to our binary search tree implementation that we considered in a previous video, then we had something like a BT node class standing for a binary tree node. And then in our BT node class, we could have a left and right pointer. And then maybe we also have a parent pointer to make it easy to get back to the parent of this node. And what we'll do is we'll just add in an extra height field to tell us what the height of this node is. And that way we can use this field to just keep track of how high, what the height is of any given node in our tree. And to do that, we could write out a really simple recursive algorithm to populate those fields. And the way it would work is as follows. So I'd call this function compute height and pass in a BT node. And then I would ask the question, is the left and right nodes null? Well, if they're both null, then that means the height of this node is 0. It's at the leaf of the tree. If the left node has a value and the right node doesn't, then that means the height of this node is 1 more than the height of the left node. And we'd call this function recursively to figure out the height of the left node first. Else, if the left node is null and the right node is not null, then I'm going to call compute height on the right node to find out its height and then add 1 to it because I know I have to be 1 more than the height of my right subtree. And then if both my left and right have subtrees, then what I want is the maximum of either the height of the right or the height of the left, and then I want to add 1 to that. And that would be the height of this node. And then when we're done, we can simply return the height of this node so that the function works recursively and properly, right? Every time we call compute height, the recursive call that called it expects to get back the height of that node so that it can add 1 to it and update its own node's height. Okay, so with this recursive function, we can easily calculate the height of our entire tree, of all the nodes in our tree. And then we can write a simple function to calculate balance factor of any given node that we need. So the balance factor would just take into account the height from the left and right subtrees, right? So if first we could initialize left and right to -1, and then if the node we pass in is null, then we can just return 0. If there is a left subtree, then the height of the left is the height of the left, the node to the left. If there is a right node, then the height on the right is the height of that right node. If either of those pointers are null, then we're just going to get the -1 value. Like I said before, it should be the default. And then we subtract left from right. And this will calculate our balance factor. Okay, so in summary, a binary search tree is height balanced if for any node in the tree, the heights of the left and right subtrees differ by 0 or 1, including -1 there. A balance factor is the difference in height of the left and right subtrees. So the height of a node can be computed recursively, and balance factors can be computed then from the height. And to make this calculation efficient, we can just keep the height as a field in each node for convenient access. Okay, in our next video, we're going to figure out how we can use this balance factor to help keep the tree balanced.